coming tonight this tech talk at Audio Analytic. I'm Sachin Kostrovich. I'm the director of A Labs, which is the research division of the company. So as you know, Audio Analytic produces software to recognize sounds. Obviously, we use machine learning for that. We use artificial intelligence. At the moment, in the landscape of artificial intelligence, there is that massive, tsunami of application of deep neural networks to various problems in artificial intelligence. One thing which is interesting about DNNs today is that people are not just looking at one architectures in isolation, so your congruitiveness or just your feed-forwardness or whatever. It starts becoming a paradigm of putting different types of architectures together. Some people call it software 2.0, some people call this phenomenon differential programming. But what's happening now is that different types of architectures which are assumed to perform various types of functionality are being put together, and then you backprop the whole thing, and then that's how you solve the problem. So we have tonight, our speaker is going to give an example of such a complex architecture which has given some really good results in sound recognition. Sometimes in the field of research you have one PhD which makes a huge difference. There is the before and the after. And that's the speaker we have tonight is Emre Cakir from the Tampere University of Technology. Thank you very much.
Thank you very much, Sasha, for the introduction. Hi everyone, my name is Emre. I recently completed my doctoral studies in Tampere University in Finland. And today I'm going to give a summary of my PhD thesis titled Deep Neural Networks for Sound Detection. So let's start with the basics here. So the definition of sound event is an audio segment that can be labeled as a distinctive concept by most people. So we're looking for broad definitions of sounds here. So examples such as doorbell, baby crying, footsteps, dog barking, bird singing, applause, alarm clock, and gunshot. These are all the sound events that we're mostly working on. So when we look at the sound understanding in humans, we notice that humans are very robust to subcategories of the sound events. These are also called intra-class variations of different types of doorbells, different types of dog barking, etc. We are very robust to these different subcategories. We also know that humans require a certain time to perceive the sound events. If we are given a 200 milliseconds of audio, we cannot tell maybe if it's a cat meowing or baby crying, but once we are given, let's say 1-2 seconds, we would perceive the sound event with almost 100% accuracy. Another one is that humans can use the sound event sequence to interpret the scene. So if there's if we hear some footsteps, some car horn, some engine noise, we cannot assume that this physical scene is probably a busy street, for instance. So our aim is to develop a system that can automatically detect these sound events. So in the light of the human, auditory recognition, we can say that this system should be robust to these inter-class variations and should also be able to utilize the temporal modeling of the events. Just a quick problem formulation for sound event detection, or SED for short. So, given a predefined set of sound events, our aim in SED is to detect estimate the start and end time of each sound event in a given recording. So here we see the list of the sound event labels, alarm clock, baby crying, etc. And on the top panel we see the time raw audio waveform, so one-dimensional signal basically on the time axis, and then we see the annotations of each sound event when they are present in this given audio signal. So our aim is to detect the event in these short segments, or we call them frames, around 20 to 50 milliseconds, and then we will combine the detections over the consecutive frames, and that's how we'll get the onset and offset for each sound event. So there are of course certain challenges for implementing an SED system in real life. Environmental noise, quite common. Peripheral factors such as room impulse response, hardware setup, etc. Intra-class variations, as we mentioned. And also related to interclass variations, high amount of label data requirements. This is because we would like to capture the whole sample distribution. We would like to get as many as different types of doorbells, etc., in our data sets, so that we can distinguish this. We can say that we can distinguish doorbells in a given audio recording. Now the rest will be about methodology. So sound event detection can be basically or often defined in the two stages. First one, sound representation. Second one, sound event classification. So in the sound representation stage, we will be extracting, we will be getting our acoustic features for our second stage sound event classification. So some of the sound representation examples are time domain audio or audio waveform, raw audio. So this is just one D signal. That's the original recorded digitally recorded signal. Would be 1D and would look like this. On the other hand, for sound event detection, we are mostly working with time frequency domain representations, since they're more compact and more informative in terms of the sound content. Magnitude and power spectrogram is one example. These are obtained using the short time Fourier transform over the audio waveform. And then maybe more commonly, mass spectrogram. So mass spectrogram is calculated and it's loosely based on the human auditory perception in the sense that humans are very reactive or more sensitive to the changes in the lower frequency range of the sounds and less sensitive to the high frequency changes. So mass spectrogram is using this fact about calculating this to the representation. The next stage is the sound event classification, as we said. So in sound event classification case, we'll be trying to find a mapping between these acoustic features. In this case, visualized as the magnitude spectrogram. So we're trying to find a mapping between these acoustic features and the sound event labels at each time frame. And for that, we could ideally engineer a method that will do that for us. So, but since this relationship is very complex, we actually don't know how to come up with an engineered solution that can map these acoustic features to the sound events. So, for that reason, we'll be using machine learning. A few words about the contributions of this thesis. So, there are two main contributions. First is to adapt and apply the currently very popular deep learning methods, such as feed neural nets and convolutional recurrent neural nets for robust SED. So we'll be contributing to the second stage sound event classification. And in the second contribution, we'll be trying to combine the feature learning capabilities of these DNNs with the domain knowledge and feature extraction using the domain knowledge. So we'll be contributing both to sound representation and the sound event classification. In the rest of the talk, I'll explain a bit about how we do these contributions by giving examples from the papers in this thesis, and also giving some background information, very short information about the we mentioned a specific method called communication. Shortly, here's a framework for sound event detection using DNS. So we would have in the training stage, we would have the raw audio and the annotations usually obtained manually, specifying the onset and offset for each sound event. So with the audio, we will extract the acoustic features from the short time frames. We will obtain this 2D representation. So one axis will be the feature axis, one axis will be time axis. And then we will obtain, from the annotations, we will get the target outputs, the binary target outputs that will show which events are present at a given frame. So this will be also this will be also metrics that one axis will be time and the other will be the classes. And then we will train a deep neural network to learn this mapping between this input and the target output. With the DNN, in the testing stage, we will get the class presence probabilities at each frame. And these values will be between 0 and 1. And we will treat them as probabilities, and then we will apply just simple binary thresholding, for instance, with the unbiased threshold of 0.5 to binarize these probabilities, and we will say that if in a given frame class A probability is over 0.5, we say it's present. If it's not, we say it's not present, and that's how we will get this class activity indicator. So the first method that deep neural network method that we'll look into is deep feed-forward neural networks. So for deep NNs, we would have the input as single frame features, so one the input, and the target output would be the binary activation vector for a single frame. The benefit of deep FNS, especially compared to these more established methods before deep learning, such as cluster mixer model, the Markov-based model-based methods, would be the high expressional capability to model complex input and output networks. And also empirically, we noticed that it gives much better accuracy compared to these methods. The minus for this method would be due to its fixed connections, it would not be robust to small shifts in frequency content, and this is a major factor in the intra-class variations. That the examples from the same sound event might exhibit some sort of certain shifts in the frequency content based on, let's say, in the case of dog barking, based on the dog's breed, etc. So, but in our deep FNS, we have the fixed connections, so we assume that the features related to the sound event will happen in the same frequency all the time. So this can be regarded as a minus. Another minus is the short temporal context, since we will be using deep FNS only use like one-dimensional input. We are either going to use some single frame, or we'll actually talk about it later. We can do some sort of like concatenation of consecutive frames to get a context windowing vector. But still, like we can't increase the number of vectors that we use a lot here a lot, and this limits the performance of deep FNS. Which brings us to our first paper in the thesis, titled Polyphonic Sound Event Detection using multi-label deep feed-forward neural networks. So here the task is real-life sound event detection with 61 classes. So we have about 20 hours of data. The term multi-label is used here, and polyphonic sound event detection is used here, meaning that we expect there can be multiple sound events happening at the same time, which is often the case in the, or sometimes the case in the real life scenarios. When we think of a busy street, we would hear the footsteps, car horns, all these different events happening at the same time, which introduces quite a challenge to the system. The motivation for using deep FNS for this task for us was, at this point, around 2014, there was some work about deep FNS for sound, and they were showing that this method is very capable of using different subsets of neurons to detect different events, and also simultaneously. So basically, we'll be using different paths of DNS to detect different events at the same time, which is a quite good benefit, quite important benefit for this. The other one is that deep FNS have been producing very good results in other order-realized tasks at this point, such as ASR and single-level sound and classification. So we thought we should try this. For this paper, our input was log Melband energy vectors with context winnowing. Context winnowing I'll explain in a bit. And our network looked like a deep FNN with 2 hidden layers, 800 units each, and max out activation. And in the output layer, we would have the sigmoid function that would produce our output between 0 and 1, which would treat as class presence probabilities. And we used cross entropy as loss function. So context winnowing basically looks like this. We'll be simply concatenating our original input acoustic feature vector with the 2 preceding and the 2 succeeding frames to get some sort of like more of a temporal information for each acoustic feature vector. So you receive xt and then concatenated with xt minus 2, xt minus 1, xt plus 1, and xt plus 2. So each of these vectors will be individual examples for the deep element. Yeah, so when we look at the results, okay, here the results are divided in based on the acoustic scene that the recording was taken. So we have again 61 classes, and then we have recordings from 10 different acoustic contexts: basketball court, beach, bus, hallway, restaurant, etc. And the evaluation that metric that we're looking for is on score. So we compared this method with the baseline GMM HMM system, and we noticed that around all the context we see a huge benefit of using Dfcns over the baseline method, and for some contexts it's almost more than double the performance, and on average 19% absolute improvement, which was quite significant at the time. Another point that I'd like to mention from this work is the relationship between the amount of annotated data for each class and that class's accuracy. So at the top panel you see the data amount for each class, and then the bottom panel you see the F1 score for that class. It's quite easy to notice that these two are highly correlated, which points to the fact that we need at least some amount of data for each class to be able to detect it in a satisfactory level. Yep. A few conclusions. So we saw huge improvements of DNS over the conventional methods. Class accuracy is very much related to data amount, and this was the first work that successfully applied the DNS for Polyphonic Scg, and for which we can say nowadays we see this with the DK's challenge. Most of the submissions are with deep learning, and this was kind of one of the first works that was using deep learning for sound detection. The second task, or the second paper, would be again using Dfcns, but in this task we are looking into the effect of the class correlation information for again real-life 61 class sound event detection. So what I mean by class correlation information is that does our network utilize this information that if class A is always present when class B is also present, then when the class A is when the network thinks class A is present, does it say also that regardless of the input or to the less information of the input, it says that class B is present too? So how much does it use this information that these classes are often found together? So our input again, log node and edge vectors with contextual knowing, as in the previous paper. So how we proceed with this work is that, so month-label DNN is the same as the previous paper that I mentioned. Combined single-label DNN would be, we will be training a deep feed-forward neural network for each class, and then at the end we will combine the outputs. So simply using the same input for training both networks, which means that you'll be giving the same input even though it includes polyphonic data. If we are training the class C classifier for single label detection, and in our input there's class A and class B, we say that there's no event present. And if we are training the class B classifier with the same input, we say that there's only class B present. So the single label classifiers should be able to basically filter out the event of interest from a given audio recording. Yeah, so there is no class correlation information in the CSL of combined single label DNN in the bottom level. So yeah, here we see the results for detection performance versus polyphony level this time. So polyphony level being how many sound events are active at a given time. So we divide this test set into this disjoint sets of based on the polyphony level. And I think there are two important factors that you can read from this figure. One would be the performance is quite close between these two methods. As you would see, the difference is not higher than 4%, at least in one case, and the average difference seems to be about 2%, which is quite. You can say it's quite comparable, these two methods. So we ignored this class correlation information from this CSLDNN, and it still works quite good. The second one would be when you look at the increasing polyphony level, what you would expect is that with the increased polyphony, meaning a lot more sound events happening at the same time, it would be actually harder to detect individual sound events, especially for CSLDNN when you think about like it's trying to detect this one sound event among the 6 sound events happening at the same time. And the performance, we would expect that the performance would decrease, but on the other hand, for both methods, it actually increases. Yeah, and the difference between these MLDN and CSLDN become a bit more evident in this high polyphonic case, which as you would expect, but still the difference is not that much. So again, a few conclusions. The performance drop was very limited, even though we excluded the class correlation information. The conclusions that are marked with blue are marked with the idea that they are maybe most related to the application or product level. So the first one would be like polyphony level increase, do not decrease the performance for either method. So if your product is focused on being able to be robust to these high polyphony levels, then this will be a good method. And the other one is the benefit of usage case flexibility with CSLDNN. So when the sound event of interest, classes of interest change, you can change the bundle of these different single level classifiers and come up with a different classifier. And when you think about like when you get new data, you know that you have this multi-label model that you know it's working quite fine for these classes, and then with this new multi-label data, you're a bit shy to train with this new data because you're worried that it might affect the performance. But if you have a separate single label classifier for each class, then you can be sure that you can keep the performance of some classes at the same level. Yeah, so the second method that we'll be looking into is deep recurrent neural networks. Deep recurrent neural networks, the simple versions of them are quite similar to deep feedforward neural networks with the additional feedback structure. So what we mean by feedback structure is that in addition to the input vector for this current frame, we'll be using our outputs from the previous frame as for calculating the outputs for this current frame. So again, so the input will be this time with features from a frame sequence, so it will be a 2D input, and corresponding to the target output will be a sequence of binary activation vectors, so a binary activation matrix. The benefit of deep recurrent neural network will be, especially for these more advanced recurrent neural networks such as gated recurrent units and long short-term memory networks, will be able to model the long-term dependencies between consecutive inputs, which is quite significant when you think about the average length of sound events, maybe 3 to 5 seconds or maybe less. But the frames that we have are only 20 to 15 milliseconds, so these consecutive frames will be quite correlated, and having the information from the consecutive frames is quite crucial for detection. The minus for this method is the same for Dfcns, which is the fixed connections basically, and them being not a robust small shifts in frequency. The third method that we'll be looking in is deep convolutional neural networks, CNNs. So CNNs differ from FNNs and RNNs in the sense that instead of connecting every neuron to every neuron, we'll be computing the activation through a local kernel, and then we will be sliding the same kernel over the input, so we have shared weights basically. So our input is again a features from a frame sequence, a 2D representation. Our target output will be again a sequence of binary activation vectors. So again, our input is a patch of mass spectrogram. You can think of it like that. The benefits of using Dfcns is the input frequency shift invariance due to shared weights, as I mentioned, and also max pooling that's also commonly used after each convolutional layer. And also it has much less number of parameters since we are sharing the parameters over the whole input. The minus would be the short temporal context. The typical convolutional kernel size in time would be less than 10 frames, basically, and it's not always enough to cover the temporal context. As I mentioned, the sound events taking multiple seconds. So, which brings us to deep convolutional kernel networks. So I explained the benefits of CNNs and RNNs. So the simple idea would be just combine them and hope to get the best of both worlds. So we will use the convolutional layers to extract high-level local shift invariant features. We'll use the current layers on top of the convolutional layers to model the long-term temporal information. And finally, we'll use the feed-forward output layer to get the class presence probabilities at each frame. So, our third paper is CRNNs for Polyphonic Scg, the most detailed paper in the thesis. So for this, we're now using log mass spectrogram. So our 2D input, as I mentioned in the CNNs. And our network looks like a convolutional layers, which rectify the linear unit activation, followed by max pooling in only frequency domain, not in time domain, because we'd like to keep the temporal resolution of our estimated outputs the same as the target output, or we would not like to decrease the temporal resolution. For the recurrent layers, we use gated recurrent unit layers, which produce the outputs for the whole sequence. And for the output layer, we use a feed-forward layer with sigmoid activation. So we apply this feed-forward layer at each frame. So the same set of weights for the feed-forward layer will be applied at each frame in the output layer. The data sets that we used to evaluate our methods were TUTSET synthetic 2016, 16 sound event classes mixed synthetically with random offset, so around 10 hours of data. TUTSET 2009, this is actually the data set that I have been mentioning, 61 class real life environment recordings, 20 hours. And so at this point we have this synthetic data set, we have this real life data set, quite large real life data set. And then as a third low research scenario, we decided to use TUTSET 2016, which has 11 classes of real life environment recordings, but only has 78 minutes of data, so it's quite limited amount of data. Okay, in this table, we see the performance of the different deep learning methods and the GMM for these three data sets. Our evaluation metrics are F1 score and error rate, and we calculate them in frame-wise level or in 1 second segment-wise. So as you can see, the CRNNs for TUTSET synthetic 2016 and TUTSET 2009, they offer a huge performance increase over both deep learning and other deep learning methods, but also much better than the previously much used established methods such as GM. And for the third data set, for the low resource data set, you see that the performance difference between these different methods are actually do disappear. And we're kind of blaming this to the low amount of data, although it's hard to tell since the F1 score levels are quite low for each method, around 27%. So definitely not at level, not at trustworthy level, reliable level medicine. Yeah. I'd like to highlight a part of the deep neural network training that I think is not getting quite enough attention. So when you train deep neural networks, in the beginning what you start with is initializing your unit weights or neuron weights with small randomly selected values. So these will be probably sampled from a uniform distribution with centered at 0. So one important factor and another point is that you'll be training your network most likely with a differentiable loss function, cross entropy, or mean squared error, etc. But your evaluation metric will be, let's say, score error rate, and these two does not necessarily follow each other. So you might see different. So combining the effects of these two, you can see a different performance by just simply changing how you initialize your weights. So you use a random seed, which means like random seed, the initial number that you'll start generating your random values, and then if you change that value, although it shouldn't matter much because you just this is not talk about much. It's just this random value that you start generating your random initial weights. But then what you'll notice is that the performance in terms of the evaluation metric changes a lot in the SCD research work, a lot, or to a certain degree. So in this work, we also try to see the effect of this and how much it defines the performance. Because the thing is, if you're so for instance, we see that RNN has the average of 52.8, but it's with the standard deviation of plus minus 1.5. So you can expect a performance in this range. So just to make the case that the performance decreases solely based on the architecture itself, and not just a random fluke of just ending up with a good set of initial random weights. And we also see that CRN is actually the most robust to this initial seed changes with the less standard deviation, and it gives the best performance. Another result from this paper is the F1 score versus sequence length for RNN and CRN. So sequence length being, so we have the patch of log-mass spectrogram as an input, and the sequence by sequence length we mean how long of a sequence that we use for a single example. So, okay, we see that CRN is actually benefiting from the sequence length, much longer sequences, much more than RNN. So RNN makes the peak around 2.5 and then starts decreasing, while CRN improves up to 20 seconds of sequence length. So the difference between RNN and CRN is the seed part. So that's what should be explaining this difference in the performances or the behaviors with the sequence length. So we can say that we can assume that convolutional layer features, the features that are extracted from the convolutional layer, are much more suitable for longer term temporal modeling than using the mass spectrogram values for each frame that we do with RNNs. So now we are a bit also interested in the performance of these methods with different conditions. So we're interested in how much, for example, pitch shifting, simple pitch shifting would affect our performances for these three methods. And what we'll do is basically we'll use the original data, so no pitch shifting, and we'll use that data for training. And for the test data, we will do simple pitch shifting with various quarter tone levels, and to see if your network breaks basically with this simple change. And we see that although all of the methods are affected by this, but CRN is not only giving the best performance, but also is the least affected among these three methods from the speed shifts. So we do not only focus on getting the best performance, but only we are interested in understanding how these networks learn. So here we see a simple example of it. What we do here is we have a trained CRNN, and we are interested in what kind of patterns that these convolutional filters are looking for in this trained network. So what we will do is we start with a random input, and then we will monitor the convolutional layer outputs for certain neurons, and we will be basically doing gradient descent in the sense that we will be trying to maximize the output of the convolutional filter, and we will do that by changing our input. So here are the final inputs that we get. So these are the sort of patterns that activate the convolutional layer the most. So you can basically say that these are certain patterns. These do not look like just random values, but there is some sort of information that each filter is specifically looking into given these inputs. Another point that I'd like to mention is about the model size. So here we see the number of parameters versus accuracy. These are from the hyperparameter grid search that we would do. So basically, a different number of layers, different number of units per layer, etc. And then normally we would just pick the best performing network for each of these methods and then report the results for that. But then we're also interested in how for example, the model size affects the performance. So with the CRNN, with the blue diamonds, you would notice that even for the very small amount of, it actually performs the best with the smaller amount of parameters, and then the performance doesn't really improve with larger model basically. For CNN it's similar. For RNN it requires some certain amount of parameters to get to the peak, but doesn't improve after that at all. So from here we can see that CRNN's domination is not just related to the model size, but with the same number of parameters we would get a better performance for CRNNs rather than CNN and RNN. So a few conclusions. Superior results with CRNN over other methods. CNN can model longer-term temporal context better than RNN. And CNN is more robust to shifts in frequency content, as we showed with the peak shift example, kind of synthetically, but that's the best we can do. So this might be related to, again, the application-specific comments about like the hardware differences, room impulse response change. These are the factors that would change the characteristics of inputs, maybe in the form of frequency shift change, etc. So we see the CNN is more robust to that. And again, CNN doesn't require a very large model for good performance. So there are two other papers of CNN from the thesis. The one is the implementation of it for bird audio detection in the context of the Queen Mary University of London challenge. So here the task was to detect if bird audio is present in a given 10-second clip, and adjusting for the adjustment that we did for this work was the temporal max pooling, basically from this frame level probability, so we would get one probability value for each clip. And the paper 5 was the application of it for application of CRNN for rare sound detection. And here, this was in the context of EK's 2017. And here we were given a 30-second recording, an ambience recording, basically, and detecting the onset and offset for either baby cry, glass break, or gunshot if they are present. So, and these events happen very rarely and for a very short amount of time. So for these papers, as I said, we use very similar method with the paper 3, but then with the paper 5, we did this extra analysis work that I'd like to mention here. So we keep mentioning that the recurrent layers are used to model the longer-term temporal information, etc. But we cannot really see that in the like the numbers that they provide higher performance, but we cannot really justify our theory like in action. So for this, we did this experiment that we used gated recurrent units again for the recurrent layers. And how gated recurrent units works is it uses a gated structure to control the information flow. So it will have this cell state and controlled by this update gate and reset gate. And the final output of the GRU will be the linear interpolation of the previous activation and candidate activation. Candidate activation will be controlled by both update gate, reset gate, and the previous activation. So the HDs are our output of RNN layer at given frame t. UT is the update gate. So what you would do is you would basically pass this recurrent layer output HT to the feed-forward output layer that you have. But then you would miss the information, how much of the contribution was coming from the previous activation, how much was from the candidate activation. So our theory is that for the rare sound event detection, when there's a new event happening, the cell state should be changed, so the reset gate should be active. Our candidate activation should be dominating the total activation. And then for the rest of the event, it should be about the previous activation. So just continuing as long as the sound event is active. In order to monitor if this is really the case in our work, we will basically apply the feed-forward output layer, but we would keep them as separate. We would keep the candidate activation and the previous activation parts as contributions as separate and apply this feed-forward layers weights to these separately. And then we will get such a figure. So in the top panel, we would have the contribution of the candidate output, C hat. So remember, this is the one that should be active when there's a new event happening, so you should update the cell state. The panel B is the previous output contribution to our final output, so the presence probabilities. C is the total contribution of these, so basically the sum of them. And then D is the probability versus time. So here, the shaded area is where the event is actually happening. And then the blue line is our predictions, so class presence probability prediction, probabilities that we have. And also for these top three panels, the y-axis is basically the neurons, so different neuron activations versus time. So what we see is, so blue is very negative values and red is very positive values. So we see these kind of 3-4 neurons in the top panel that are mostly very negative, but then they're active right at the time when the sound event starts happening. So these are the neurons that are doing the job of resetting the cell state. And they're also, again, not active after that. And in the previous, on the panel B, we see that the contribution of the previous output, so they are then the dominating parts of the total output after the initial resetting is performed. And with the combination of these two, we get the almost perfect, or I guess even perfect estimation of the position of the sound event. Finally, a few words about the second contribution. So here we look at the feature learning through end-to-end CRNs. So we see that our current acoustic feature extraction methods are mostly agnostic of the task. You would calculate the mass spectrogram the same way, almost the same way, for the task of automatic speech recognition, chord recognition for music, or sound detection. So they're agnostic of this task. But they're not guaranteed to be optimal for SCD. Okay, they reflect the fact that of the human auditory recognition, but we are not 100% sure it's good enough for sound event detection, or if these two are just the same thing. And the most common ones, which are the perceptual-based representations, they're empirical and they're listener-specific. These stem from about 50-year-old subjective listening experiments that were a bit problematic with the hysteresis effects, etc. So they're not 100%, but they are just being used by everyone just as the default sound representation as such. And there's not much research going on in this field for sound detection. So our proposal was to, but anyway, for their credits, the mail spectrogram works quite well, like compared to other sound representations, and people maybe didn't just see the need of playing with it. So our solution is, we acknowledge the fact that it works quite well, but we use it as a starting point. And what we will do is we would have we would integrate it to a deep neural network. We will integrate the acoustic feature extraction to a deep neural network to obtain ad hoc feature extraction methods. So we have 2 papers on this. I will mention in this work the second paper, end-to-end polyphonic sound detection using CRNs with learned time frequency. So it looks like this. So we keep the same CRN part, as we have shown it works quite well. What we add here is we use the raw audio as input, but we would be doing basically the acoustic feature extraction using the neural network layers. So these are simple like matrix operations and elementary operations that you can easily implement in the form of deep neural network. So how we would do it is that we would initialize the neural network weights to extract STFT initially. But then we'll be doing the training for this whole thing jointly for both CRN and the feature extraction part. So our assumption is that we will be getting, by updating these feature extraction parameters based on some loss function for SED, we will get a more optimal sound representation. So yeah, here we see the results. Okay, there are three different methods here basically. So using the DFT or the magnitude spectrogram for input, keeping the parameters fixed or learning them. So keeping them fixed would be the same as using magnitude spectrogram as an input for CRN. And we do the same for MEL spectrogram and log mass spectrogram. So the bad thing is that, as you might notice, the fixed ones, so the more pale colors, are almost always better than the more sharper colors, which means that our initial assumption was actually not helping. Just keeping them fixed is doing the job better than making these feature extraction parameters learnable. What we have noticed otherwise was that some contradiction with how the MEL, for example, MEL spectrogram is calculated and how we had our final feature extraction parameters. So the difference is that in the MEL spectrogram, the changes in the lower frequency range is more emphasized, so we would have more filters in the lower frequency range and less filters in the higher frequency range. So the assumption here is that the higher frequency level changes has less effect on the sound event detection. So we investigate this by taking the magnitude spectrum peaks for the real part of the weights. So what I mean by that is, so here you have the real DFT layer. So they are basically sinusoids with different central frequencies, and cosines with different central frequencies. And what you will see here is that when you take the magnitude spectrum peaks, it will be basically an impulse train over the frequency. So you would have basically dots around the ones initially. And then when you do this at the final network, what you will notice is this one. So we take the DFT at using different sampling rates. What we notice is that the filters over about 4K, they are not much updated at all. So, which actually confirms our assumption that these also non-spectrograms assumption that these inputs to these information is not much helping to sound wave detection. So, information after 4 kHz. But what's also interesting is that some of the filters in the lower frequency range are actually de-emphasized. They're deemed detrimental to the sound wave detection, which is kind of different than mass spectrogram, because for mass spectrogram we'll be emphasizing the lower frequency range by using smaller filters on that part. So you wouldn't be de-emphasizing them. But here, for example, we can assume that around 800 Hz we have the more detrimental effect for the sound wave detection. So which brings us to our final conclusion. So we see the comparable SED performance, but not the SED performance through network weight initialization with the domain knowledge. And final acoustic features differ significantly from these common methods such as mass spectrum. We also noticed that the learned filter bank frequency response can be useful to find out which frequency bands matter most. So what you can utilize this information is maybe adjust quantization for different bands. So you can decrease the number of bits that you use for representing your higher frequency content, and you can change the number of bits for the low frequency content, and you can basically also de-emphasize, as it was learned here, some of the content. This is all ad hoc, so depending on your data set. Another final conclusion is the sound detection performance was comparable, over 60% F1 score, even when we decreased the sampling rate from 44 kHz to 8 kHz. So here we see already over 60% F1 score, which again gives the information that the over 4 kHz we have this information. So yeah, here's the list of publications used in the thesis. We have 7 publications there, and if you're interested, you can find the PhD thesis publicly available. If you just Google Crns and my name with deep neural networks for sound wave detection, and here's a link also. Yeah, that was the answer. Thank you.